As has been previously demonstrated, in the monitor only and monitor and control sections, it is possible to calculate the volume flow passing through an array or measure a pressure differential in the air delivery system using feedback from a pressure transducer. With the MDC controller, we can also use this data to vary the fan speed as the basis for closed loop, constant volume, or constant pressure control. In the case that a single pressure transducer is used for flow or pressure measurement, the output of the pressure transducer can either be connected to the control input terminal of the MDC controller or to the analog input terminals on the fan, AN1, IO1, or AN2, IO2. For volume flow, the negative pressure port of the transducer should be connected to the inlet ring measurement tapping, and the positive pressure port should be connected to a measurement point in the suction side plenum. It is important that the measurement point in the suction side plenum is positioned in a still, non-turbulent area to avoid errors caused by the measurement of dynamic pressure. It is also possible to measure a pressure differential using a single pressure transducer connected to the controller or the fan analog input terminals. In an application that requires protection from ingress of pollutants, it may be desirable to positively pressurize the room or building and control the pressure downstream of the fan in comparison with atmospheric pressure. In an application that requires containment of pollutants, it may be desirable to negatively pressurize the room or building and control the pressure upstream of the fan in comparison with atmospheric pressure. When an air handling unit contains an array of multiple fans, the air tubes connected to the inlet ring pressure tappings can be joined together to create an averaging pressure circuit. For this system, it is recommended that each of the branches of the averaging circuit are of the same length to the point where they join to prevent an inaccuracy due to a measurement bias and ensure that a true average is being measured. With a control system that uses a single pressure transducer, whether it contains one fan or several fans with averaging pressure measurement, there is a reliance on a single component to provide the required feedback to the MDC controller. This means that there is no redundancy should the transducer be damaged or stop working. If redundancy is required, in case there was a loss of sensor feedback to the controller, the control system can be changed to include multiple pressure transducers. Multiple pressure transducers can be connected to the analog input of the fan control, AN1, IO1, or AN2, IO2, and read by the MDC controller over the RS485 communication network. Each fan can have its own individual pressure transducer to provide feedback to the MDC controller, or the sensors can group together several fans in the array using an average pressure measurement circuit. Where multiple fans and pressure transducers are used, the MDC controller adds up the calculated volume flow or averages the pressure differential readings to compare against the set point and adjust the fan speed accordingly. In the case of the loss of a transducer, the MDC is programmed to raise an alarm condition and will use the reading from the remaining sensors to continue controlling the whole fan array. In the following examples, we will demonstrate the closed-loop constant volume control capability of the MDC controller. In this example, we are using the smaller 2-fan air handling demonstration unit that has a pressure transducer measuring the pressure difference between the suction side plenum and the fan inlet ring pressure tappings. The pressure tappings on both fans are joined together to produce an average pressure reading, and the output of the pressure transducer is connected to the control input terminals of the MDC controller. With the controller in monitor-only mode, as when the network is first initialized, we use the back button to return to the main menu. Choosing the operation mode option, we can select constant volume or constant pressure. The pressure transducer in this case should be set to read at the controller. And in this example, we will choose volume flow, set the pressure range of the transducer to 2000 pascals and the K factor of the inlet ring to 76. Once entered, we can then set the desired volume flow set point, in this case 1200 meters cubed an hour. After a reset, the controller will adjust the speed of the fans until it reaches a steady state at the set point. If the intake louver is adjusted to create more pressure for the fans to operate against, the measured volume flow will decrease and the controller will increase the fan speed to compensate. To simulate a blocked filter condition, we can increase the pressure by closing the louver further, and the extra resistance causes the measured flow to drop and the controller increases fan speed to attempt to return to the set point. If we then change the filter with a clean one, release the pressure restricting the flow through the fans, there will be a measured volume flow which is much greater than required. The controller will then slow down the fans to return to the set point at a much reduced speed. In the next example, we are using a larger air handling demonstration unit that has 4 fans, each of which has been fitted with an individual pressure transducer, measuring differential pressure between the inlet ring pressure tapping and the suction side plenum. The output of each transducer is connected to the analog control input of its associated fan, and the MDC controller is calculating the volume flow through each fan individually, adding them up to calculate the total volume of air passing through the array. The fans that we are using are Modbus Lite versions, and we will be reading the transducer output signal from analog input 1. In this example, we are using the larger demonstration unit with 4 Modbus Lite fans, each with a pressure transducer connected to its analog input A-in-1U. With the controller in monitor-only mode, as when the network is initialized, we use the back button to return to the main menu. Choosing the operation mode option, we can select constant volume, constant pressure. Where multiple sensors are being used, the pressure transducer should be set to read at the fan analog input. In this example, we will choose volume flow, set the pressure transducer range at 500 pascals and the K factor of 76. Once entered, we can set the desired volume flow set point at 2,500 meters cubed an hour. After a reset, the controller will search for the transducers installed at the fan analog input terminals. The MDC looks for all of the fans that have been connected to a sensor output, and the user can then check that the number of sensors found matches the fan array setup. In this case, all 4 fans have a pressure transducer connected. The user can choose to accept the sensor map, after which a reset is performed. The MDC then adjusts the speed of the fans until it reaches a steady state at the desired set point. In this final example, we are using a larger air handling demonstration unit that has 4 fans in 2 groups of 2. In each group, the inlet ring pressure tappings have been connected together in an averaging pressure circuit and connected to the negative pressure port of the pressure transducer. The positive port of the pressure transducer is connected to the suction side plenum using a pressure hose installed in a still, non-turbulent area. The voltage output from the transducer is connected to the analog input terminals of one of the fans in the group. This connection method has created a dependency where one fan is providing the output data which is read by the MDC and the other one is responding only to the speed commands received from the MDC over the RS485 network. In this configuration, the MDC firstly detects the number of sensors fitted to the fan array. If there are fewer sensors than there are fans, the MDC will determine which fans are connected to which sensor by running each of the remaining fans in the array individually. Once this installation routine is complete, the MDC will know which fans have a sensor installed and which fans are additionally contributing to the averaging pressure circuits in the fan array. The MDC controller can then calculate the volume flow of each circuit by multiplying the measured volume flow of the fan reporting the pressure differential by the number of fans that are connected to the averaging pressure circuit. The MDC then adds the volume flows from each averaging measurement circuit together to calculate the total air volume passing through the array. The fans that we are using are Modbus Lite version, and we will be reading the transducer output from analog input 1 terminal on the fans. In this example, we are using the larger demonstration unit with 4 Modbus Lite fans and 2 pressure transducers connected in averaging pressure circuits. With the controller in monitor-only mode, as when the network is first initialized, we use the back button to return to the main menu. Choosing the operation mode option, we can select constant volume or constant pressure. Where multiple sensors are being used, the pressure transducer should be set to read at the fan analog input. In this example, we will choose volume flow, set the pressure range at 500 pascals, and the K factor of the inlet ring is 76. Once entered, we can set the desired volume flow set point at 2,500 meters cubed an hour. After a reset, the controller will search for the transducers installed at the fan analog input. The MDC initially looks for all fans that have been connected to a sensor output. The user can then check that the number of sensors found matches the fan array setup. In this case, there are 2 fans that have a pressure transducer connected. On finding fewer sensors than fans, the controller then operates the fans without the pressure transducer connection, one by one, to determine which transducer it is sharing. The user can choose to accept the sensor map and the shared dependencies, after which a reset is performed. The MDC controller then adjusts the speed of the fans until it reaches a steady state at the set point. If the intake louver is adjusted to create more pressure for the fans to operate against, the measured volume flow will decrease and the controller will increase the fan speed to compensate.